Okay. Hello everyone. My name is Baojian Zhou. I'm a postdoc researcher at Stony Brook University. In this video, I will present our work, online AUC optimization for sparse high-dimensional datasets. And this is the joint work with Professor Yi Yin from University at Albany and Professor Steve Skinner from Stony Brook University. Okay. I will first introduce the motivation and problem formulation, and then I will present our proposed algorithm for FTRL-AUC. Finally, I will discuss the evaluation results and make a conclusion. Okay, so what is online AUC optimization? So online AUC optimization is to maximize the AUC score and the online learning setting, where the learner receives data samples on the fly and maximize its AUC scores. And it is favorable when the data streams are imbalanced. By imbalanced, I mean the number of the negative training samples are much larger than the positive ones. And this setting, it is more favorable to maximize the AUC compared with minimize the error rate. So there are many real-world applications that use AUC as the performance metric, such as a online CTR rate prediction, email spam filtering, and identifying malicious URLs. Okay, for those type of the datasets, training samples are usually sparse and high-dimensional. So what does this mean? Suppose training sample X is in D dimension, but it has key non-zeros. But this key is much smaller than D. So for example, in the CTR rate prediction, an advertisement is the training sample X. The dimension is 1 million, but there are only 15 non-zeros in average. So current online AUC methods have two drawbacks. First, the per iteration cost are OD time. And second, the learned model are usually not sparse enough, which could be an issue. So the research question that we want to ask is, can we design an algorithm so that the per iteration cost can be reduced from D to K time, and at the same time, the model is sparse and effective? And I will answer the question positively in the following slides. Okay, problem formulation. So to formulate the problem, let us first define the AUC score and online learning setting. So the learner receives a sequence of data samples, xi, and labels yi. So x plus are positive training samples, and x minus are negative ones. So we can define AUC score in this equation, and it can be interpreted as the probability of a positive training sample ranked by a linear classifier W higher than the negative training sample. So we have a toy example of calculating AUC score in this figure. The green line, as you can see, the green line is the linear classifier W. For each of the training sample, the W can define a ranking score, and then we can calculate the AUC score accordingly on the figure right. Okay, so to optimize the AUC score, the learner's goal is to find a linear classifier W that maximizes the AUC score defined in this problem. And clearly, it is equivalent to minimize 1 minus the AUC score, that is, minimize this objective. But in an online learning setting, it is difficult to minimize this objective due to two facts. First, the indicator function is not differentiable, and second, the objective is not positive-wise decomposable, which I will explain later. So in the following section, I will propose our algorithm for FTRL-AUC and present key ingredients of our proposed algorithm. Okay, first, to make the objective differentiable, we choose the least square loss as our surrogate so that it can be inconsistent with the 0, 1 loss. So the second one, which is our key observation, is that online AUC optimization is equivalent to a set point problem inspired by our previous work. So this lemma says that the problem 1 here, defined here, is equivalent to the following empirical set point problem. So this new formulation tells us that the objective can be decomposed into the sum of individual loss ft. So each ft only depends on one training pair, xt, yt, so that we can update the model in an online fashion. But the per iteration cost to solve this set point problem is at least a d operation. So in the following 2 slides, I will show you how can we define a new loss that we have a sparse gradient, and that sparse gradient is a key to reduce the per iteration cost. Okay. So our first key ingredient is we define a new convex loss ft hat, and this equation is the definition of ft hat. It is essentially based on the ft. So here we have 2 estimators are important, AT and BT. As you can see, AT and BT is the ranking score of all positive training samples and the negative training samples in average. And we need to D operations to calculate the AT and BT. I will discuss this later. Okay. So our theorems. So this is our main theorem. Our theorem tells us that ft hat is convex, and the gradient of ft hat is sparse. So what does this mean? It means that if the data training sample xt is sparse, and then we can calculate the gradient like this way. And this is essentially the scaling of the xt. And then the gradient of ft hat is also key sparse. And the rest of the challenge is how can we efficiently update AT and WT? Because PT here, we can calculate it out at a constant time at per iteration. Okay, so this leads to our second key ingredient. We proposed a new lazy update rule. Let us recall AT, BT here is the definition of ranking score of all positive training sample and the negative training sample in average. So take AT as an example, and we can rewrite it as the following. So what we do, what we essentially do is we split this inner product into 2 parts. This is the ranking score of all previous positive training sample in average, plus the second part is the ranking score of current positive training sample. So in the approximation step, we do a lazy update, which is essentially taking a step back by replacing WT by the WT minus 1, so that we can update AT recursively by using this equation. So the key ingredient here is that per iteration, that we only need to calculate the inner product of WT with current positive training samples. And we can finish this per iteration cost in key operation. And similarly, we can update BT like this way. Okay. So you may wondering, a lazy update rule may hurt the performance of the algorithm. But in our experiments, we found that a lazy update rule is empirically robust and effective. So this figure shows you the convergence of the AUC score with respect to the number of the training samples seen. And we compare with the measures for lazy update rule and the measures without the lazy update rule. And there are 2 important observations. First, as you can clearly see, with lazy update rule shows in the red lines, it is more stable than the one without using it. And the second observation is that using lazy update rule, it could be faster, especially at the early stage, as you can see in this figure. Okay, so our last key ingredient is we try to incorporate the follow the regularized data filter framework to update our model so that we can get a sparse model during the learning process. So essentially, for each time t, we update the model WT by minimize this objective. And this minimization can have the following closed form, which essentially at each step we use the calculated sparse gradient and updated the ZT, and then we can update the WT accordingly. Because here the gradient is sparse, and finally the per iteration cost can be finished in key operation in total. Okay. So here is our algorithm description. So the input, we have two initial parameters, the initial learning rate gamma and the sparse regularization lambda. So for per iteration, we receive a data sample xt, yt, and then we can calculate the ranking score and the AUC score accordingly. So from line 4 to line 14 is to calculate the sparse gradient GT, and from line 15 to 19 is to use filter framework to update the model so that we can get a sparse model, and all of the operations can be finished in key operations. So the per iteration cost can be reduced from OD to OK time. Okay. So to evaluate our algorithm, we compare our methods with baseline methods on 7 real-world datasets. So for each of the datasets, we use 2 such samples for training and the rest to pass for evaluation and testing. Okay, so we have 2 experiments. The first experiment is we try to compare filter AUC with the AUC optimization based methods, and our second experiment is we try to compare our method with the logistic based methods. Okay, so in our first experiment, we try to compare the running time with the baseline methods. This table shows you the running time after we see all training sample once. As you can clearly see that in most of the datasets, the filter AUC is 100 times faster than the baselines in most of the time. And the bottom figure also shows you the running time with respect to the AUC score convergence. Okay. So our second evaluation is we try to compare the AUC score on the testing dataset and compare with the baseline methods. The SP AUC is the best on most of the datasets, but our method is always run up on all of the datasets. And the gap between the best one and our method are quite small on most of the datasets. And one reasonable reason to explain why the SP-AUC is the best is the SP-AUC used much faster learning rate, 1/t, but all other methods are using 1/square root of t, which is a relatively slower learning rate. Okay. Our third evaluation is we try to compare the model sparsity. To evaluate the model sparsity, we define the sparse ratio as the number of the non-zeros divided by the data dimension d. So as you can see, the filter AUC learns much sparse model as shown in this table. So the smaller values means the model sparser. In the bottom figure shows you the sparse ratio as a function of AUC score. As you can see, when we try to tune in the sparse regularization parameter, when we try to increase the regularization parameter, you can see FTRL-AUC still learns higher AUC score, but all baseline methods are decreasing very fast when we try to increase the sparse regularization parameter. And it means that FTRL-AUC has a better trade-off between sparsity and model effectiveness from this figure. And our second experiment is we try to compare FTRL-AUC with the logistic-based loss. We compare with 3 baseline measures, and all baseline measures are using logistic loss, and we compare them on 2 real-world datasets, and we run the experiments 10 times and take the average and report the AUC score in this table. One interesting finding from this table is that the AUC score, the FTRL-AUC learns a higher AUC score compared with FTRL-proximal, where the only difference between those 2 methods is that FTRL-proximal uses logistic loss, but FTRL-AUC use the AUC objective. Okay, so we also plotted the sparse ratio as a function of the AUC score and compare with those logistic-based methods. And you can clearly see that when we try to optimize AUC, we clearly have benefits compared with minimize the learning rate, which is the FTRL-proximal did. Okay, so our last experiment is that we applied the FTRL-AUC on a real-world applications where we try to predict CTR rate in a real-world dataset, and we try to compare our method with FTRL-proximal. And you can clearly see that especially at the early stage, FTRL-AUC learns a better AUC score during the learning process. And the x-axis is the number of training samples seen, and the y-axis is the AUC score. And here you can clearly see there are a big gap between those two. Okay. So to make a conclusion, first we proposed a faster AUC optimization algorithm named FTRL-AUC based on generalized FTRL framework. So by using a new lazy update rule, we can reduce the per iteration cost from D operations to key operations, which can significantly reduce the running time as shown in our experiments. And our second advantage is that our model has better trade-off between sparsity and model effectiveness. So compared with FTRL-proximal, FTRL-AUC could be a good alternative for high-dimensional imbalanced datasets. Okay, so if you are interested in our code, datasets, and baseline methods, you can find all of the items from my GitHub website. And thank you for your listening. If you have a question, you can ask me a question, and I'm happy to answer your question. Thank you.